All right, we are back for our second lecture with chapter 29, and it's a little tricky, so I do want to do a bit of a review. I'm actually going to go back through a number of the items that we discussed and we introduced in the earlier lecture. So the first thing is, it's got this title called Faraday's Law, but what it really is about is generating electricity. So let's generate electricity, could be the title for this chapter. And we said the simplest way is just to have conducting materials moving through magnetic fields. Now we've looked at these examples. So I'm going to move on here. We said that we could move conductors back and forth in a magnetic field, and that would result in an AC generator. And that's it. It really is that simple. Now, there's some formulas that we've worked through here showing the magnetic forces that are going to come into play whenever we move a conductor through a magnetic field. Those magnetic forces are going to generate currents. They're going to generate EMFs. So the first step was to determine how much of a voltage are we going to get. And we said, in general, any conducting material moving through a magnetic field, whatever length is passing through the magnetic field, times the field strength, times the velocity, that's going to give us the voltage or the EMF for that generator. We can now hook that generator up to any kind of a circuit, and it's going to behave the same as a battery would. So this provides us an alternate EMF source. And then we said that here was an example. We ended up showing that if we moved a conducting piece back and forth through a magnetic field, that the forces would reverse, and that would result in an alternating EMF. And we were able to find what would be the properties of a generator that would give us our standard 120 volts, 60 hertz operation, and we came up with at least one possibility for how a generator like that could be built. And then we said that we have to push a generator. A generator's not going to generate electricity all by itself. There's actually a resistive force. Once we hook a generator up to some type of device and have current moving through the wires, here's our light bulb and here's our generator, we found that the current moving through the magnetic field sets up resistive forces. That means that we have to keep pushing on the generator to keep it in motion. The mechanical energy that we invest shows up as electrical energy, and the light bulb goes on. Here was a numerical example that we did with that. So again, just want to step back through this. This is just a reminder that we have to put a force into this. Now what we said at this point was that everything seems fine. We've got our generator, we've run some examples, everything seems to work. And then the textbook starts bringing in this idea of Faraday's Law. Now, Faraday's Law is another one of the Maxwell equations. We said that we've already looked at Gauss's law, we've looked at Ampere's law, and now Faraday's Law, it's another theorem that shows us how fields will be related. How are the electric and the magnetic fields related? What I always feel is important is that it's not a causation theorem any more than Gauss's law or Ampere's law is. What it is it's showing that whenever, whatever we do to alter magnetic flux, at the same time we can't help but generating electric fields at the same time. And those electric fields, or the magnetic fields, are going to give us an EMF. So let's move on with that. We went through, we introduced what we meant by magnetic flux. So we'd seen kind of something similar to it with electric flux. And then the textbook provides this example. So they go through and show that assuming Faraday's law, we can show that the EMF generated by a conductor moving through a magnetic field is BLV. Well, we already derived that. So, and again, as I mentioned in lecture 1, textbooks tend to do this in reverse. Rather than introducing the direct approach to start out, which I think is by far easier, they start with Faraday's law, and then they make it seem like the direct approach is kind of an afterthought. So we've done it the other way. We've done the direct approach first, and I hope that looks pretty straightforward. You just take a conductor, move it through a magnetic field, you're going to get an EMF generated in that. But now we're back looking at this theorem and trying to see how Faraday's law could be used. Here's a picture that is a good reminder of how we calculate flux. If there's an angle between the area vector and the magnetic field vector, then we're going to have to introduce a cosine of theta factor. So flux is going to depend, here's another example we looked at, as far as orientation. These are loops of wire being rotated through a magnetic field. Now in this case, you could say, well, we could use a direct approach and just see how all of these loops of wire are, what their velocities are through the magnetic field. But that's a good example where maybe Faraday's law is going to be easier. If we actually calculate this in terms of magnetic field and magnetic flux, probably easier to use Faraday's law. So again, it's kind of like Gauss's law and Ampere's law. There are going to be situations where, with particular symmetries, where Faraday's law is going to enable us to calculate EMFs that may have been more difficult otherwise. Here was another example that they gave us. This was some loops. We turned this into a constantly rotating example and determined what the peak EMF would be. Came in at 25 millivolts. Here's another example of a simple example, I guess, of, well, there's got to be an EMF generated here, because what we can do is, if we pull these wires, we can see that wires are moving through magnetic fields. Are we going to get a net EMF, or is the EMF's going to cancel? And Faraday's law guarantees us if we rotate this, I guess that's what's happening here. So what's happening is we're rotating these loops. There was a lot of flux here. There's not as much flux here. That guarantees that we're going to get some kind of an EMF. Will generate current. So yeah, you can just take loops of wire in a magnetic field, rotate them. Current's going to get generated in those wires. We said as far as keeping track of directions, again, I guess I'm going to depart with I'm going to provide a different approach. The textbook uses what's called Lenz's law and says that the EMF will generate a current in the direction that opposes the changing magnetic flux. So here are the rules. You can read through those. You can see those also in the textbook. Here are a couple of examples. We had an example of our own, and what I introduced was the idea of, rather than using Lenz's law, you can go back and use the definition of the area vector. So when I calculate a flux, I'm going to be using an area vector. And the way the area vector works, if I've defined the area vector into the board in this example, then my right hand curves in the direction of positive rotations. Whereas if I use my left hand, it's going to keep track of the negative direction. So it's kind of like, if this is the direction of the area vector, my thumbs, then my right hand is keeping track of positive rotations, my left hand is keeping track of negative rotations. That's how our coordinate systems are set up. We use these definitions of positive and negative angles and positive and negative rotations. So again, you can use just the area vector itself in order to keep track of the direction of the EMF. And the key here is to take a look at the flux and say if I have a flux that has a positive slope to it, we said in this example, let's turn up the magnetic field, and then let's let it level off for a while, and then let's let it drop back down. If that happens, then the flux is doing the same thing. And since the time derivative of the flux is first of all positive, and then 0, and then negative, well, the EMF direction is given by determining the sign overall. If d phi dt is positive, the EMF will be in the negative direction. If d phi dt is 0, then the EMF is 0. If d phi dt is in the negative direction, as in dropping off the flux, then the EMF will be back in the positive. We also took a look at pulling this object outside of a magnetic field. And we talked about both approaches. We talked about defining flux using Faraday's law. Faraday's law predicts the EMF will be minus dLV. But we said that a direct approach gives us the very same result. And actually the direct approach also immediately tells us the direction. So for example, here is this loop and it's just leaving the magnetic field. So the only region of these four sides that would be generating an EMF would be right here. And going back to that very first diagram that we wrote, keeping track of the direction of EMF says that if it's a velocity here and the magnetic field is here, then the direction of force on positive charges is in that direction. So the EMF being generated is here. And that says that the direction of the current is going to be in this direction as this, as it leaves, as this exits the magnetic field. So I would say look at the direct approach first, and then use Faraday's law as a fallback when you encounter these kind of problems. All right, I think that takes us most of the way through everything that we looked at. I was kind of a quick review. I hope a few places where we slowed down helped to maybe clarify and remind you guys of what we had talked about in the previous lecture. So here's an electric generator. Now we've already talked about electric generators as, you know, pieces of wiring that are being rotated through magnetic fields. And when you rotate through the magnetic fields, what that's going to do for us is it's going to produce EMFs, first of all in one direction, and then back in the other direction. Now if I've got this generator that's rotating, what I'm going to need to be able to do is make contact with those wires, and that's what these brushes are doing. So we've got some metal contacts, some brushes that are connected to the two ends of those wires, and as we rotate this through, we're picking up that alternating current. So this would generate an alternating EMF and an alternating current simply by rotating these rotors or the armature through the presence of these magnetic fields. Now, what's always interesting is when we talk about generating magnetic fields, what's going on inside the magnet? And if you think back to chapter 28, remember, which wasn't so long ago, what's happening with the north and south magnets is I have a bunch of electrons that are spinning. So in any diagram, when they say, oh, there's a magnet here, that's generating a magnetic field, that's almost too easy. You've always got to remind yourself, well, what does that mean? Why are the magnets magnetic? And it's because you've got electrons that have a preferential spin direction. The spins are not canceling out. There's an alignment with some of the electron spins. So that's an interesting effect. What it's saying is, if I take charges and move them nearby other charges that are spinning, here's a bunch of charges spinning, we move a wire past those spinning charges, and it generates a force on the electrons and the protons in that wire. So groups of spinning electrons lined up ends up exerting a force. That's what we're using to generate these EMFs. When we say, you know, just put it in a magnetic field. It's kind of like the magnetic fields are easily available. But it's good to understand what's going on with that. All right, so with an electric generator, what we can do is, if we have an electric generator and we're spinning the wires around in the field, and we looked at one of those examples, a similar example earlier, we can say that the flux is B times A times the cosine of an angle. And so since the angle is varying, like omega t, what we can do is we can take a derivative, using Faraday's law, we can take a derivative of that and say, look, when I spin the generator, the magnetic field's not changing, the area is not changing. What's happening is it's the orientation that's changing. So as I spin my generator, the orientation of the generator changes, and if it's being spun, then we can represent that orientation as cosine omega t, where omega is the constant rate at which the spinning is taking place. And that gives us a formula BA omega sine omega t. Now if you're worried about keeping track of which is sine and which is cosine, which is sine, it doesn't matter, right? If we represent the EMF as a sine function or a cosine function, that's just a question of where we've designated t equals 0. So either a sine or a cosine function in these problems is going to give us the same alternating effect. Now what's important to us though, so we do have this alternating effect taking place. We want to know what the peak EMF is. Now we looked at that again in that very first example. The peak EMF is going to depend on how much magnetic field we've got, what the area is of our loop, how fast we're spinning the generator, and then it depends on how many loops we've got. So up until now, I think we've just been looking at one loop, and as I always mention, I always lose track of the number of loops in problems. That's one of those things I have to circle to make sure that I don't forget about it. So here's an example. It says I've got an AC generator. It's a 60 hertz generator. It's going to be spinning at 60 cycles per second. That's pretty fast. I'm going to be using a 0.150 Tesla magnetic field. The coil, the wires that we have, now it doesn't matter what shape we put those loops in. So whatever area is enclosed within each of those loops, this one is 2 times 10 to the minus 2 square meters. How many loops are we going to need if we want to get our peak voltage of 170 volts? And remember, that's what our outlets are. Our outlets are rated at 120 volt RMS, but the RMS is an average, and it's an RMS specific type of an averaging. And the peak values are going to be 170. They're going to be larger by a square root of 2. So here's the problem. So it says, here's my electric generator. This is my EMF formula as a function of time, and I've sectioned off what the peak value needs to be. Now, the RMS value is 120, but the peak value is going to be 170 volts. Now, it's 60 hertz, and the 60 hertz becomes rotational velocity of 377 radians per second. The cross-sectional area, they told us, was 2 times 10 to the minus 2 meters squared. I just wanted to see what that was in centimeters. It says it's about 200. And so, you know, you've got something this size, so the loops, is that 200? 10 times 10 is 100, maybe. So maybe it's about that size. I've got loops this big. I've got an axis of rotation. I'm spinning the loops. And the magnetic field, you know, is determined by how many electrons we have that are aligned in those two magnets that are outside. And then I can just solve for n. So I'm taking this equation, solving for n, so I get the EMF divided by BA omega. Taking a look at all the units, checking all the units here, I'm ending up with 150 loops. So there you go. That's how many loops I'm going to need in that generator. Now, when problems talk about loops, a couple things to be aware of. Sometimes they say that the loops kind of extend out to where they form a solenoid, right? So I could have loops that are spread out so that I get a solenoid. In other problems, we're just assuming that the loops somehow, miraculously, are all following the very same path. So in this case, we would probably imagine that they're all following the same path. So it's a pretty flat stack of loops that we're thinking about. And that's an electric generator example. So now we said with the AC generator, we have this voltage that's varying in an alternating fashion. If we hook up the brushes differently, we can actually create the effect that the voltage is always in the same direction. Instead of switching back and forth from one direction to the next, it always comes out at the same direction. And then the one on the right has even more contacts and more separate loops of wire that can smooth out the EMF even more. So we're getting something that's getting closer and closer to a constant voltage. Now, when we let's go back and think about electric motors. We saw electric motors back, I guess, chapter 27. Electric motors and electric generators sound pretty similar to me. They sound like they're almost the same device. It's a bunch of loops inside a magnetic field. Now, what does happen with an electric motor is we send current into the windings of an electric motor. So the wires inside, instead of spinning the wires and generating an EMF, in a motor we intentionally send current through the wires of an electric motor, and that generates a torque. Now, once those wires are moving in a magnetic field, though, there is an EMF that's generated opposing the EMF that we're putting in. So, for example, we could model it this way. What we could say is that we have an EMF. So here is our EMF, 120 volts, and we're using that to operate our motor. So we're saying the motor has a bunch of wires inside, and that combined is 5 ohms. But what happens is when the motor starts spinning, that motor is going to become a generator, and it's going to create an EMF that's opposite to the EMF that we're using to try and boost to create a current through the motor. So that makes motors in some sense kind of fragile devices, because motors are designed so that they're going to get to some speed as they, so let's say the motor is at rest, we turn it on, and little by little the motor comes up to speed. Now the back EMF that the motor is generating depends on how fast it's spinning. So initially there is no back EMF, and the wiring in here is experiencing the entire 120 volts. And that says that in a motor, when we first turn it on, there's a possibility of a current getting really high. We could burn out the motor. So here's the problem. So they're saying that when we're operating a motor, those wires that are spinning in the motor actually become effectively a generator. And so now I turn this into AC, but the DC may make it easier to think about. So I'm going to have an alternating current that's operating my motor. And in the motor, what's going to happen is I'm going to end up with this back EMF that's opposing it. So initially, at least, I've got 120 volts divided by the 5 ohms. and that's giving me 25 amps of current. 24 amps of current. So I've got 24 amps of current initially through that motor. Now once the motor has come up to speed, once it's operating at the speed that it's designed for, it's going to actually have 108 volts opposing that. And that means that now the motor is actually being driven by a net of 12 volts. Instead of 120 volts, the motor is actually being driven by 12 volts. The current has dropped down to 2.4. So when I was a kid, there used to be phonographs and record players when you listen to music, and I liked getting out the phonograph and putting records on there and playing them. And of course I would like to hold the turntable, and my dad would say, don't hold the turntable, you're going to burn out the motor. And I thought, that's just one of those parent things, right? They just don't want you having any fun. And then finally I went off to college and learned about it, and I thought, oh, that's it, that's what happens. So if you've got a motor that's operating this simply, and there's no safeguards that have been designed in the circuitry, if you hold and stop the motor, what that does is it eliminates this back EMF, and all of a sudden you're back at this really high current. And if the wiring is probably not designed to operate at high current for extended periods of time, you burn out the motor. Okay? So if you've got something, you know, power tools or whatever, that you operate with electric motors, don't hold them. If you do, turn off the power or something. You get too much current, you could burn out the wiring. Here's another picture of, here's a more complicated picture. When you start taking electrical generators apart, they're more involved than kind of the simple drawings that we've drawn. In automobiles, alternators are used rather than DC generators, so it's an AC EMF or an AC power supply that's used in an automobile. But that's what these generators and alternators look like. All right, we want to take a fairly detailed look at transformers. So you've probably heard of transformers. I understand there's even been a series of movies made about transformers. I haven't gotten out to watch any of them. In fact, there's a whole, I mean, transformers are really cool, but I don't understand a whole series of movies based on transformers. Anyway, transformers look something like this. Transformers are used to be able to easily switch between high voltage and low voltage. So it's a very simple device. What we can do is we can take, well, typically a block of iron. So we're going to have some kind of block of iron. It'll be laminated so it's not conductive or whatever. So we're going to have some a block of iron, and then what we do is we wrap wires around many times. Now this only shows 3 or 4 windings, but it could be hundreds of loops on one side and hundreds of loops on the other side. So, and again, what transformers allow us to do is to go in and easily switch from a lower voltage into a higher voltage, or from a higher voltage into a lower voltage. And there's reasons that we want to be able to do that. So first of all, let's kind of orient ourselves. This is the primary set of coils, of loops. That's the secondary side. Now typically the primary coil is defined as the side where the power is coming in from. So here's the power coming into this transformer, but instead of continuing the wires through, we actually make a break in the wires. And so there's a set of wires on this side, there's a set of wires on the other side. We have a number of loops, or a number of turns, in the primary. Same thing in the secondary. And the voltage on the two sides, the voltages that we end up with, are proportional to the number of turns that we've built into the transformers. All right, so let's take a look and see how this might work. So here's a problem with a transformer. Now, in this example, oh, I'm sorry, it's not a, this is still looking at the operation of the transformer. So here's the transformer here, and what I've got is I've drawn in these loops. Here is the iron block that we've mapped out here. Now, what's going on in the transformer is that we're going to have current operating on the two sides. So I don't need a direct connection. I can actually use the current coming in on the primary side to induce or create a current on the other side. So that's kind of interesting. I don't need a direct connection between the wires. There's actually a gap here, but we can induce currents on the other side. Now, it turns out that we can draw these currents as being in phase with each other. And so if there's a sine function on this side, then there's a sine function on this side describing how the current is varying with time. Now, we do have to have alternating current to get a transformer to work. What happens is, if I send in direct current here, what that will do is it will set up a magnetic field inside the iron. Now, the reason that we have the iron core is that anytime we use current to set up a magnetic field in a particular region, very likely the magnetic field is pretty localized. By using an iron block, what we can do is redirect the magnetic field. Again, we're using those spinning electrons. So electrons don't mind this. They're able to realign themselves without a lot, we don't have to invest any energy in doing this. So we can set up the magnetic field here, and these electrons throughout the iron will align themselves with a particular orientation. Now, if it's direct current, then a constant current here sets up a uniform magnetic field inside, and if I have a constant uniform magnetic field on the secondary side, that doesn't create an EMF. From Faraday's law, I know that in order to create an EMF, one way I can determine how much EMF I'm going to generate is by keeping track of how the magnetic flux is varying. So I need a variable magnetic flux, not a constant magnetic flux, in order to get an EMF set up on the other side. If I can get an EMF set up on the other side, then I can drive current. Now, the way a transformer works then is once it's operational, I've got currents happening on both sides. Since I'm driving this with an AC current, then I'm getting an alternating magnetic field. Now that's kind of remarkable too. I got a magnetic field that is switching directions 60 times a second. It's a pretty rapid switch back and forth, but iron doesn't mind doing this. The electrons inside there don't mind realigning themselves 60 times a second. So iron's pretty responsive, doesn't have a problem keeping up with a 60 hertz variation in the orientation of those spins. So current generates varying magnetic field. Varying magnetic field creates varying flux. And I know if I have a variable flux that an EMF will be generated on that side. Now within the iron core, let's think about how much magnetic field we actually have. We can treat each side of the iron core as if the magnetic field there is given by 4 pi k over c squared n1 over L times I sine of omega plus side 2. So the magnetic field that's going to exist inside the iron, at least the portion of the magnetic field that's due to the currents, is going to be a combination of the effects from both sides. So it's not just that we're setting up a magnetic field with these loops. These loops also are going to be generating their own magnetic field. So I'm going to end up with a combined magnetic field. Now the iron is actually going to reinforce that magnetic field, and it's going to direct it. So it's going to make sure that both magnetic field effects are experienced throughout the entire loop. Now, I wouldn't have to build a transformer like this. Instead of making a block of iron like this, I could take these loops and just run them through the iron here. This way it's easier to see. It's easier to see the two loops on this side, but and then have kind of an O-ring set up for our transformer. All right, so again, current coming in, oscillating. Current going out is oscillating. The magnetic field inside is switching direction 60 times a second. Okay, and by saying the magnetic field is changing, that means that electron spins are switching back and forth, aligning themselves in one direction, and then the other direction, and then the other direction, back and forth 60 times a second. Now, each of those, well, the magnetic fields that we have, each of those contributions to the magnetic field is going to contribute to the flux. And so I can also combine the flux from both sides. The primary and the secondary, both of those have flux being generated. And so each loop, if we say each loop has a cross-sectional area of A, then each loop of wire on each side experiences this full flux. So it's like both sides are contributing to the flux, and every loop on the primary and the secondary side experience that flux. Now we can come in with Faraday's law and say that the EMF across this side of the transformer is going to be given by the number of loops times the rate at which that flux is changing. Same thing for the second side. We can use Faraday's law to say that the EMF is going to be equal to the number of loops times the rate at which that flux is changing. Since the flux is the same throughout, and the variation, the oscillation pattern is the same throughout the transformer, that says that the d phi dt is the same on both sides. And it really just comes down to number of loops. At that point, the voltages on the two sides, I've got this listed as EMFs, but I guess I can write those as voltages, are proportional to the number of loops. And that's how we vary the voltages on the two different sides of a transformer, is we can just change the number of loops on the two different sides. So, here's kind of the big picture of everything going on. Here is the power plant. We're generating electricity. Let's say that the generators are actually operating at 12,000 volts, not 120 volts, but 12,000. Well, it turns out that if we transfer electricity over long distances, which we do, you know, you see transmission lines that are hundreds of miles, it's more efficient, we'll see why, it's more efficient to operate at really high voltage. So what we do is we make transformers. We can jump from the 12,000 volts up to 240,000 volts. That's a step-up transformer. And I can do that by, what's the factor here? So there's a factor of 20 to 1. I want to get the voltage 20 times as large in order to transmit compared with the voltage at which the generators are operating. And I can do that by putting 1,000 loops on one side of my transformer and 20,000 loops on the other side. Whatever ratio of voltages I need to boost up or drop down to, I just want to make sure that I have that same ratio of loops on the transformer. So we're going to have a 20 to 1 loop ratio. That gives us a 20 to 1 voltage ratio. And then we're going to transmit all of this energy. People don't want outlets in their home at 240,000 volts. That's too many volts. That's too dangerous. So what we're going to do is we're going to have a substation that drops us from 240,000 down to 2,400. Aha! That's down by a factor of 100. So now we're down, and we can use transformers again. So I used transformers to step up the voltage, transmitted the electricity, used another transformer to step down the voltage, down to 2,400 volts. Now 2400 volts are those highest wires on the electric transmission poles. The ones that say high voltage at the top, I think, are the 2400 volts. And then once you get down into neighborhoods, occasionally, intermittently, you'll see another step-down transformer that brings everything down to 240. So let's see what the ratios are. This was 20 to 1, so maybe this is 1,000 loops, this is 20,000 loops. Here we've got 100 to 1, that may be done in a series of steps. And then this last step down, we're stepping down by an additional factor of 10. And we can do all of that just by counting the loops of wire on the piece of iron. So that's it. That's kind of the big picture as what's going on here. And see, they haven't written this as EMFs anymore. They're just writing it as voltages. So the voltage on the secondary is to the primary as the same ratio of numbers of loops. The numbers of loops are going to determine that for us. Now, what happens, you might be thinking, well, wait, how do we go up to higher voltage? Doesn't that represent more energy? And voltage alone is not the whole story. So it turns out that the current, whenever the transformer boosts the voltage, it drops the current. So voltage and current are oppositely related here. And so if the voltage goes up by a factor of 100, the current drops by a factor of 100, and the power is maintained. So transformers can be, 100% efficient pretty much. So let's try an example of this. Now this isn't a big, powerful transformer. This is a little transformer in some kind of electronic device. It's one of those transformers that you plug onto the wall. And the wall is at 120 volts, and it's alternating current. Remember, this is not going to work if it's DC. So we're going to start off with a 120 volt AC source. That's the outlet. I plug in my transformer. And the other side of that transformer comes out at 5 volts. And what this is, it's a cell phone charger. And it is going to charge the 3.7 volt battery that's in my cell phone. So my cell phone's at 3.7 volts. I'm going to use this 5 volt AC to charge it. Now that's not the whole story. It says there's also diodes in there, which we talked about. No, not yet. So never mind. We haven't looked at diodes yet. To keep the current going in the same direction. Okay. So they're giving us some numbers here. Let me go ahead and just take a look at the solutions that I had written up. So here I am trying to take all the numbers they've given me and solve this. So here's my transformer. My primary side is at 120 volts. My secondary side is at 5.00 volts. And the key feature here is, remember, all of our transformers, we're going to treat them as ideal. So the power in matches the power out. And that says VI in matches VI out. Voltage times current. That's the rate at which energy is coming in. And then V times I is the rate at which energy is leaving. So I'm going to make use of that. Here's the other information. So they told us that we want to step down from 120 volts down to 5 volts. Now that's a factor of 24. So we're going to decrease the voltage by a factor of 24. What's going to happen with the current? And the current's going to get a boost by a factor of 24. Now here it says what we want coming out is 700 milliamps. And the number of loops on this side is 30. So I'm setting up some of these ratios. What I'm going to do is, first of all, I did want to go in and check the power. So the power that I see coming into my charger is 5 volts at 0.7 amps. It's a 3.50 watt cell phone charger. That's the rate at which it's able to take in electrical energy. Now that's going to be the same on both sides, so just to be clear. Now if we start stepping down, let's go down and see how many loops we're going to need. N1 divided by N2 has to match V1 divided by V2. And since this is a ratio of 24, I'm going to need 24 times as many loops over on this side. So on the primary side, I want 720 loops. That's taking the 30 multiplying by 24. Now as far as the current is actually going to be 24 times less. So that came in around 29 milliamps for the current on that. So we've got all the numbers calculated. And then we can go back and double check, you know, these are the voltages, currents, and numbers of loops on the primary side. And then these are the voltages, currents, and numbers on the secondary side. And when we go through and check powers, what we're seeing is we're getting 3.5 watts coming in, 3.5 watts leaving. So that's what we would expect to see in a transformer problem. All right, let's take a look at long distance. Let's kind of go back to that picture that we had before. Here's another problem that they've given us. So it's kind of that same thing with the power plant and the transmission lines. And what's happening here is this. Here's the power plant. Here are the high voltage lines. And then as we come in close to the neighborhoods, we're going to use some transformers to step things back down. Now, what we're showing in this example is why is it that we want to go to such high voltage with those high voltage lines? It sounds dangerous. Why would we want to do that? Well, we want to transfer a lot of energy, and what we know is that the wires themselves are going to heat up. And if we think back to chapter 26, the amount of heating in some wiring is going to depend on how much resistance they have and how much current is going through them squared. So the thermal energy that we're going to lose is 0.40 ohms. That's what they've told us the resistance is, times 500 amps. Now I got to switch back over here. So first of all, it says what would happen if we were to run the transmission lines at 240 volts. Well, the town, it says, needs 120,000 watts. And if we run the lines at 240 volts, that says we're going to need 500 amps of current. Now, if I send 500 amps of current through those power lines, then the amount of thermal energy that we generate, 500 squared times 0.5, that's 100 kilowatts. So how much energy is, or how much power is the town using? Well, the town's using 120 kilowatts. How much thermal energy, or thermal power, am I going to generate getting that to the town? Well, that doesn't sound very efficient. I'm only getting 120 kilowatts to the town, but I'm using 100 kilowatts just to transmit the electricity. So the idea is, why did this happen? And that's because the current was so high. You know, the thermal losses within the wires, which are basically resistors, it really depends on I squared. So if there's a way to bring the current down, we could save a lot on thermal energy. Now the way to bring the current down is to boost the voltage. So here is the town now. It still has the same energy needs, same power, but this time we're going to have the wires operating at 24,000 volts. So, you know, here's the transformer leading into town, and this side of my transformer is going to be at 24,000 volts this time, instead of at 240 volts. This time, instead of 500 amps, I only need 5 amps. 5 amps is nothing, right? Now, at 5 amps, when I come back and calculate the thermal energy losses in my transmission lines, my electricity transmission lines, it's at 10 watts. So how should we build our power supply systems? Should we operate at high current and lose half of the energy along the way? I guess what that comes down to is we have to generate twice as much energy. So because, the town's going to get 120 kilowatts, but since the wires are going to use half of that, we're going to have to generate twice as much. Or what if we make the thermal energy losses in the wiring completely negligible? And that's what we do. So we build transformers so that we're not just heating up the wires constantly and losing all of that energy. We can also build wires that are a reasonable diameter. With this much thermal heating, we got to make the wires bigger if they're going to carry more current. So who knew? You can go to high voltage and then very efficiently transmit your current. Now, if transformers are going to enable us to do this easily, so this is where transformers come in. We can use transformers to step up the voltage, and then transmit the electricity at high voltage, and then bring the voltages back down. And then transformers are only going to work if we're operating with AC current. So why do we use AC? So that we can use transformers, so that we can transmit the electricity at high voltage, so we have minimal energy losses in the transmission of electricity. So that's kind of what's driving this whole idea. Now when the current does come into your house, here is this 2400 volt line, and here's a transformer up in the neighborhoods. This side is at 240 volts, and so what we run, the wiring coming into your electric box in your house or your apartment or whatever, is coming in at 240 volts, but that's split. What they do on that side of the transformer is they don't just have these wires at 240, but they have one in the middle called the neutral wire, which officially they designate as 0 voltage. So this neutral wire actually gets grounded, literally, into the ground. You run a wire with a long copper grounding conductor and pound it into the ground so that this stays at neutral voltage. Well, what that does is it puts one of these at plus 120 and one of these at negative 120. Now this is AC, so what we're saying really is that it's alternating back and forth in any case. But if we now hook up different appliances in our house, let's say I have a high energy use appliance, like a range or a clothes dryer, those are going to require the full 240 volts. So in that case, we use these two wires to maintain 240 volts across those appliances. Now, most of the outlets that we have in our house are set at 120, so if it's not one of those high energy need appliances, then almost everything else is operated at 120 volts. So we have a 120 volt between these two wires, and we have 120 volts between these two wires. So that's kind of how it works. Now, you can actually run two different circuits off this set of wiring. What you can do is you can have two different circuits share the same neutral wire. Let's have it set up like this. Let's say that here is one of my hot wires, and so these are often black. The neutral is supposed to be white. Hot wires are the black ones. Sometimes they're red. So when they share these two sets of wiring, often one is black and one is red. What this enables us to do is, here is something that is operating off circuit 1. So I have a circuit breaker here to make sure that I1 doesn't get too large and damage my wiring, maybe cause a fire. And then I have another circuit, circuit 2. It's got its own resistance and it's got its own current. Now, because of the way that AC is connected up to the transformer, if current 2 is running in this direction, current 1 is running here. And what happens in the neutral, if we call that I0, that neutral wire will have a current that is the difference between I1 and I2. So that's why instead of having two distinct circuits, two of these circuits can actually share this neutral wire. Because of the phasing effect here, that middle wire will never overheat. If I'm using both circuits, then most of the current is going around the entire loop. If I'm just using this circuit and R2 is turned off, then the current comes back through the neutral. So the neutral wire can be used in either direction with either circuit. So kind of interesting wiring, just you know, a little familiarity with how the wires are coming into our house and how that how everything's connected. All right, I am going to now. This is Faraday's law. Faraday's law is wonderful. What Faraday's law does in many situations is allows us to measure changes in magnetic flux and relate those to an EMF. Now an EMF in this case, it's not being written as EMF, it's being written as E field dot DL. It turns out these EMFs that we're talking about, they're actually due to electric fields in many cases. So when we're using Faraday's law, electric fields are being generated. Now here's where I take issue. You guys are required to take critical thinking, right? Isn't that one of the English classes? And they go through the list of common fallacies. And one of the common fallacies in critical thinking is assuming that because two things happen at the same time, that somehow they're causal. That A is causing B because every time A happens, B happens. And that's not necessarily true. So it is not the case that magnetic flux creates an electric field. It is the case that when I try and change the magnetic field, that happens by varying the current. So I've got a current operating and it's generating a magnetic field, and when I vary the current, the charges are accelerating, and that means that I'm generating acceleration fields, electric fields. So again, I feel like, you know, the physics community has gotten into this bad habit. There's kind of a list of things that we've gotten used to explaining a certain way, and at best they're misleading, and in many cases I think they're just wrong. And so it's not that the varying magnetic field is creating this, it's that whenever I observe a changing magnetic field, I know that what is creating that magnetic field will also generate an electric field at the same time. And that's what Faraday's law is keeping track of. So when you hear these things about changing magnetic fields cause electric fields and changing electric fields cause magnetic fields, I'm going to say rubbish. What happens is we have charges that are accelerating that are creating both effects. So we went over these before, and so we should already be familiar with these velocity fields, but just a reminder how the acceleration fields operate. And if I have charges that are undergoing an acceleration, they're going to generate E fields that wrap back around the direction of acceleration. They're also going to generate magnetic fields that loop, and the magnitudes of these fields are proportional to how large the acceleration is. They drop off like 1 over r, not like 1 over r squared, and they're equal magnitude. Now over here we said that typically the electric fields dominate and the magnetic fields are not as large, but here the electric and magnetic field components, due to the acceleration effect, exactly match. Now if we apply this to wiring, what we can do is say, okay, here's a piece of copper wire, maybe it's made out of copper. Let's define a charge density. So lambda, my charge density or charge per length, I'm going to say here's a short segment, ds, and there's a certain number of charges in there because of free electrons. So dq ds gives me lambda. Now a current could be thought of as a charge density times a velocity, and a di dt, a current that's increasing or decreasing, has a di dt to it. And what that's equal to is, and there should not be a square here. I have no idea where that came from. I clearly drew it. This should be, we're taking a derivative dv dt. There's not a 2 there. This is lambda times a. So now I'm calling this j just because I feel like di dt is in many ways just as important as I. There's two effects going on. If I'm running current through a device, not only is I important, but di dt is also important. So what happens is this. If we have a constant current, well, a constant current is like having charges moving with a constant velocity. And what that will do is it won't generate an electric field at all. Because what happens in a piece of wire, I have charges that are moving, but I also have the protons, I have the electrons moving, the protons are also in there, and the two effects cancel out. So if the current is staying constant, that doesn't give us an electric field, but it does give us a magnetic field, and that's what the X and O's are showing here. Now, if we have a di dt, now a di dt, I guess I'm calling it J over here, and it doesn't have a square. Take that square out, I'll have to take care of that in the notes. If I've got a current that's picking up speed, I am going to get E field lines in the opposite direction. And that's what many of these effects that we're looking at, when they talk about Faraday's law and changing magnetic fields are creating electric fields. It's not the changing magnetic fields. What it is it's the accelerating charges. So when charges are accelerating in one direction, electric fields are generated that run opposite to the accelerating charges. If I now put other wires nearby these, if I put wires next to each other and I accelerate charges in one, it will create an EMF in the opposite direction of the ones nearby. So accelerating charges will set off current in an adjacent wire. That's how current induction takes place, typically through accelerating charges. So here's an example. Here is an induction range top, and this is presented as an example of changing magnetic fields or generating electric fields. But what we've got down inside, down below that oven top, are currents, AC currents, large AC currents that are moving back and forth. So if I've got charges going back and forth, those are accelerating charges. And what they'll do is they will exert forces on the electrons inside my cookware. So the cookware, it's metal, it's conductive, and so current inside the pans begins to become induced. So currents run back and forth inside the cookware heats up, and that's what cooks your food. So this induction effect is coming from accelerating charges setting other charges into motion. Now there's one final example that they have here. Let's take a look at this. What they're saying is, here is a solenoid. It's got N loops spread out over a distance L, and it's got some kind of a diameter or radius to it. Now the AC current that we're using in this solenoid is the magnetic field that's being generated is 4 pi k of c squared n over L I sine omega t. That's the solenoid formula that we've looked at. And so the current we're using here is oscillating, and that was what was given in the problem. If I now take this solenoid and I turn it on its side, what's happening here is I've got current running around the side of this solenoid, And since it's alternating, that current is accelerating. So there's an acceleration taking place of those wires. And what will happen is when the acceleration is in one direction, there will be an opposing electric field set up due to those accelerating charges. Now, it's easier to use Faraday's law to solve this problem. So let's say that we have a magnetic field times the area, the cross-sectional area for the magnetic field is pi r squared. That gives us a flux, 4 pi k over c squared, n over L, pi r squared, I sine omega t. That's a lot of notation to keep track of. But again, what's happening here is I'm generating an electric field that will be opposite in direction to the acceleration of those charges. But I'm using Faraday's law to first of all identify what magnetic fields are generated, and using Faraday's law to figure out what sort of electric fields are being generated. So to use Faraday's law right here, so I'm going to find a closed path that circulates around my solenoid, and I'm going to integrate the electric field along that path. So this is beginning to look kind of like Ampere's law, right? Integrating along a path like that. That's going to give me E times 2 pi r. And then I'm going to set that equal to the time rate of change of the entire flux. Now when I take the time derivative, all the constants are still there. The sine function becomes a cosine, and I bring out a factor of omega. So again, this is out of phase. It's gone from a sine to a cosine, and I have an additional factor of omega. Collecting everything together and solving for E, it's that equation at the bottom. And that's going to take 5 minutes to read, but it's minus 4 pi k over c squared, n over L, pi r squared over 2 pi, omega I. Now I put the 1 over r here by itself. I thought that was interesting. What it's saying is the E field is going to get less and less as I move farther away from the center of this solenoid. And again, this is one of those approximations. We started with an approximation assuming the solenoid's really long, and that says that this E field formula is really only going to work in regions pretty close to the solenoid, but that's it. So that's what the E field is. And now if I take a loop of wire, let's say we take a loop of wire and surround it, that loop of wire will have current induced inside. Due to the presence of that electric field, there's going to be a current induced in that wiring. All right, a lot of stuff I know in this chapter to take in. Here's another example of a sound system. So there's a fixed magnet, and by having little bits of current go through these wires, so this is a speaker membrane. What's going to happen is that membrane is going to move back and forth. So again, we can use currents, and the magnet, a reminder too that the magnet consists of a bunch of electrons all lined up, spinning in some direction. And so they're going to interact with other electrons that go by and either be drawn towards the magnet or pushed away from the magnet, and that will set that membrane into motion. So could be a speaker system. All right, here's our summary. So I have to go through and change all the wording on this. Let's see. We learned how to generate electricity, how generators are going to work. We said that there's a simple direct method that we can use when possible, but there's other times we're going to be using Faraday's law because sometimes when things get more, the geometries get more complicated, it's harder to use the direct approach. Anyway, the textbook is assuming Faraday's law is the first one you look at. I'm going to say, no, don't go to Faraday's law first. That's your backup. Now, if I do use Faraday's law, this is how flux is defined. This is how we determine EMF by getting flux as a function of time, and then taking derivatives. Now again, I got to cross out all the causality statements. No, it's not the changing magnetic flux that creates the EMF, but it is a useful way to determine. We can carry out the calculations that way. Let's see, changing magnetic fields produce, and cross that whole one out. General form of Faraday's law is in terms of an electric field. So that's pretty cool. It says, okay, so getting back to your critical thinking class, these two are correlated, and what correlation means is whenever this happens, but these are not causing each other. They're both caused by a separate effect, and that's accelerating charges. Okay, so accelerating charges is creating both of those effects, and those effects are correlated. We're not going to get this electrical energy for free. We're going to have to use mechanical energy. Here are the formulas for my transformers, ratios of voltages and ratios of current, inverse ratios of current, are related to the number of loops, and takes us through chapter 29. So we're going to be moving on. We're going to actually, a number of the things we talked about here are going to stay around in chapter 30. But we're going to get back into looking at circuits. So AC circuits in particular should be fun.